Okay, let's start from the point where we stopped last week. We discussed about the symmetries, right? The symmetric operations or uh, different types of symmetries that we can observe in crystals, right? So the first one, or one of those is rotational symmetry, right? Translational symmetry, right? And the other one is point symmetries. Right. So anyway, we'll first take again, just remind the translation symmetry, where we can see the repetitive unit. This repetitive unit, if you translate to some distance in a direction, right? Uh, for example, like this, it can still preserve the repetition, right? It does not change the uh, it does not change the shape of the unit cell, right? The smallest unit that represent the repetition does not change. For example, you can see here, you can put it up to here, you can move it up to here, but still you can see the preservation of the shape. And also you can do the same, right? So like this, we can have the translation symmetry. And the other one, we can have the mirror symmetry, right? Mirror type of symmetry that, when you have a plane horizontal, right? In the last week slide, there was a mistake, right? So I have corrected it now. You can see it should be a horizontal plane, right? So the mirror image, exact mirror image, you should be able to see. So that means we call it mirror symmetry. If the mirror is in vertical direction, still you can see the symmetry. Okay, right. Uh, another possibility is you can combine these two. For example, you can put a vertical uh, plane here and get the symmetric operation done, and another uh, plane you can put to make it uh, reflected again. But you see, uh, after two uh, two operations, you will see the object is like this, right? Uh, in some operations, you can see the object shape uh, is exactly a mirror, right? Reflecting here a mirror, because you see H is here, right? H is here. That is how you can see the mirror image. Again, in some cases, even though you put the mirror, still you see the same order of the element. For example, H, I, O, right? The same order. The elements are in the same order. But in the previous case, elements are in the opposite order. H is the first here, but in the original object, H is the last here, right? So this type of changes can happen, but still the object is in symmetric shape. Okay. So anyway, these type of symmetries can also be called bilateral symmetry, not only in biology but in uh, other cases also. You can call it bilateral symmetry, right? So that is mirror symmetry. You can observe these type of symmetries in crystals. And the other one is inversion. We call it inversion, right? So this is also one kind of a reflection actually, but in a point. Remember, it's in a point. It's not a reflection over a plane like in the previous case. So in that case, this is mirror symmetry, but this is not mirror symmetry, because you see, if it is mirror symmetry, for example, if you had the object like here, then you should see that particular object uh, like this, right? This corner should come over here, right? but in this case it's different. This corner is down there in a different place, opposite place, right? So this is called inversion. Because of that, it's called inversion, right? This is inversion. So you see, you can project actually. It's a kind of a projection. So this point can be projected along over a point, right? So it goes up to here. And this point, you can project it to here, like this, right? So this is how you can see the inversion in a point, right? So all corresponding points you can see in equal distances. All the corresponding points are in the equal distance locations, right? All in equal distance locations. So this is a feature. This is the feature of the inversion, right? So you see, all these points are equally distributed in distances given equally either side of the point. So this is the point along which you can see this inversion, right? So this is one another kind of a symmetry. But if you take the object itself, right? For example, if you take an object like this, it does not have a proper symmetry, right? So for example, here you don't see normal symmetry is not there in this object, right? You can't divide it into equal halves, so it does not have a symmetry. But by the inversion, you can make this object a symmetric object, right? So if this is a crystal, if this can grow naturally, right, this might give you some kind of a symmetric shape uh, in terms of its after growing, right? So you have one face here and another face exactly similar type but in opposite direction. So uh, in 3 dimension, this can be a symmetric object, right? But the symmetricity is along this point, right? It's over this point, right? So this is what you call the inversion. So the point we call center of symmetry, right? The point in the interior here, we call the center of symmetry. Okay, right. The other type of symmetry we considered was rotational symmetry, right? What is rotational symmetry? Rotational symmetry is rotation. After rotation, it should be showing some kind of a symmetry. For example, this object can be rotated, okay, and this can be rotated, and this also can be rotated, right? Then we will see the same type of the object without any distortion, right? So even this you can see after rotation. Right. So in this case, this rotation is how much this rotation? Can you think of that? Yes. Anybody? How much that rotation was in a angle, right? So it's a originally it was like this. So we rotate it and we make it rotated like this, right? So then 180 degree angle. The rotation was that much. What about the second case? The rotation to get the same shape. How much do you have to rotate this? This has to be rotated how much? Has to be rotated 120 degree, right? When you have 120 degree rotation, you see the same object. Okay, so this angle, you have to rotate the object, entire object equivalent to this angle, right? This is 120 degree, right? In the previous case, you rotated it over this angle, that is 180, right? So this angle is 180 and this angle is 120, right? So if you rotate it only 160 degree, sorry, 120 degree, you will see this shape again, right? So what about this one? This is easy, right? So you just rotate how much? This amount, right? This is 90 degree. This is 90 degree. After rotation of 90 degree, this object will show you the same shape. And this one, if you rotate this in this angle, what is this angle? This is a hexagon. Should be 60 degree, right? So this should be 60 degrees. So when you rotate it in a 60 degree circle, angle, what would happen? It will give you exactly the same shape, right? So depending on this angle, right, the symmetry is defined for each object, right? So this one, uh, this angle is important, right? So this is 180, this is 120, and this is 90, this is 60. So what each of these operation represent? If you rotate it in a full circle, that means 360, right? That means 360. So actually, 100 degree, 180 degree rotation, you see the same object means when you rotate it again 180 degree, you should see the object again, the same repetition should take place, right? So if in this case, if this is 120 degree, so when you rotate one time 120 degree, you will see the same shape. And when you rotate another 120 degree, you should see the same shape again. And another 120 degree, you will see the same image, right? So in this case, three times you can see uh, the same object. So you can see three times, okay? In the previous case, how many times? Only two times. What about the third case? 90 degree. So how many 90 degree rotations, times can you see the same object? One time, one time, one time, one time. That means four times, right? So if you rotate it throughout 360 degree, there are four occasions where you see the same shape, right? So here also you see four times. And this one, ideally, how many times? Should be six times, right? When you rotate it over a 360 full circle, you will see the same shape, same object in six occasions. In six occasions. So we call these type of rotation. How many times that you see the same object over a 360 degree rotation is called the n-fold symmetry, right? We call it n-fold symmetry, right? So how many times you see over a 360 degree rotation, if you see it in n times, then you can call it n-fold symmetry, right? So in the first case, you saw it two times, right? You saw it two times. That means this is two-fold symmetry. This is two-fold symmetry. In the second case, you saw it three times. That means it's three-fold symmetry. The fourth case, you saw it in the 90 degree case, third case, you saw it in four times. That means four-fold symmetry. And the last case, you saw it in six times. That means it's six-fold symmetry. So rotational symmetry, you can define as how many times, based on that, you see the same object. How many times you see the same object during the rotation over a full rotation circle, 360 degree rotation circle, right? So this is called the n-fold symmetry. But if you see some object, for example, like this, right? Uh, it's just called one-fold symmetry, but actually there is no symmetry for that. One-fold means nothing, right? Uh, no rotation, and you don't see the object. I mean, at only at one time you see the object. That means you can't repeat it. There is no repetition. So if there is no repetition, that means it's not symmetrical, right? So you can't call it a symmetry. So there is no one-fold symmetry. Okay. So two-fold, three-fold, four-fold, five-fold, six-fold, or like that. You can have. These are called n-fold symmetrical patterns uh, with respect to rotational symmetry. Always remember, along an axis this rotation has to be done. Okay, along one axis, right? Along one axis, or along the same axis you see this number of times of rotation, the symmetrical configurations. Otherwise you can't define it as a symmetry, right? So this is called the symmetry axis. This is called the symmetry axis. So this axis is also important, the symmetry axis, right? So did you understand? Any question? Okay, right. So there is another type of a symmetry. We already discussed it. That can also have n-fold. That means n times, depending on the object, like in the previous case, right? It can have n times. N times, because we can have n time rotational symmetry, right? So the next type of symmetry we are going to discuss is a combination of rotational symmetry plus another one, right? So therefore it can have this all these combinations n-fold symmetry, right? So therefore we call it n-fold roto. Roto means rotation, n-fold roto. So it includes n-fold rotation plus another operation, that is inversion, right? So you know the inversion before, right? This is inversion. So rotation plus inversion is called roto inversion, right? So this roto inversion is also a combined type of a symmetry. So a combined type of a symmetry. So the object will be transformed into itself. That is the important point, right? Object will be transformed into itself. That is the meaning of the symmetry, right? After the following two-step operations, right? If you consider 90-degree one, this one, if you consider the four-fold symmetry, right? For example, if you rotate it 90-degree first, right, along the symmetry axis, and then you have to do the inversion with respect to a point of the axis, right? So what you do is you first rotate it, right, 90-degree, for example, in this case, right, and then you do the inversion, right, 90-degree rotation. After uh, after that, what you do is inversion, right? So you do the rotation and then you have to do the inversion. For example, you take uh, these two elements, right, together. So you rotate it 90-degree, right? You rotate it 90-degree, and then you do the inversion. So you do the inversion, you will see uh, this type of its location. So what do you think after this rotation and inversion? What is shown here? You have the triangle here. Again, you have the triangle here. You have the square here in the same orientations, right? You have the square here, right? The same orientation. I mean, there is no upside down, right? The same orientation. So what did you do? Two symmetrical operations you did. One is rotation and then inversion. So which is usually equal to the mirror plane symmetry, isn't it? So you automatically make it into a mirror plane symmetry after two operations. After one stage of rotation and then followed by inversion means you can directly compare it with the mirror symmetry. The same symmetry will be found. So uh, two-fold rotation symmetry, sorry, not always. Here, yeah, we did fourfold thing, right? We did fourfold here in this case because we are having a square here. So you rotated and inverted. Then what was the resultant situation? You got the mirror plane image. So you can have the same try with this object, with this set of objects, right? And see whether you get the exact mirror plane after these two steps of rotation. Okay. So you check it with yourself. You can take two pieces of papers, written this set of letters, and try doing these operations. Right? You may have to do in two two steps, but the combination of steps might be confusing. So you have to do uh, several times. Then you will find at two stages you can find the rotation, correct rotation. Okay. So that is how you define it, roto inversion. So always remember, roto inversion is providing you a, mirror plane symmetry at a certain stage. Okay, so we discussed about the symmetries with different operations, right? So different operations, we call it symmetry operations because they are macroscopically visible. What is macroscopically visible? That means it's visible in uh, bigger bigger scale. You can see it even with your naked eye. You don't need any microscope to see that, right? But some translational symmetry, in some cases, you will have to use electron microscope or something, or even optical microscope, probably, right? Because you with the naked eye you might not see the translation. It's just when, because it is angstrom scale, I said once before, right? Very if it is in angstrom scale, then you don't see that atomic scale, right? But these operations, the other operations, they are macroscopically visible. So all the crystals, you can see these type of symmetries. All these point symmetries are possible to see. So reflection in a point is called the inversion. There you have a center of symmetry, right? Remember, one point was there along. Through that point only we can project our points to the corresponding place in the opposite direction. That is called the center of symmetry. And then we have the reflection in a plane. That is what we call the mirror symmetry. And rotation, right? Then the rotation about an imaginary axis, right? Because symmetric axis is not physically existing, right? So we have to take an imaginary axis to rotate the object. So that is what you call the rotational symmetry, one fold, two fold, three fold, like that. And then we can combine two operations, that is rotation and inversion. Rotation and after it, inversion, right? So that will give you roto inversion. But later you realize that roto inversion also give you the same mirror symmetry also, right? So these are the symmetric operations that you can do for a crystal. Okay, right. So these symmetric operations let us define uh, the point we call basic symmetry elements, right, in crystals, right? Because we can combine these symmetries and find out uh, elements in crystals, right? So that will be useful to classify the crystals, right? So depending on these symmetries, different crystal systems can be classified. So that's the point of using symmetries. So symmetry is important because from one system to another, the symmetry is different. So if you have a different symmetry, I mean two crystals with two different symmetries, that indicates they belong to different crystal systems. Okay, so this is one important aspect that we can uh, arrive at using the symmetry elements. So one fold rotation, you saw the rotation through 360 degree, but actually there is no real symmetries there because there is no one fold symmetry. Okay, because object will repeat into the same shape after 360 degree means you have actually nothing done to the object in terms of symmetry. It's the same object, right, in the same orientation. But if you are getting the same object on the way, uh, halfway through, or uh, more than that, like here, then you can call it asymmetry because you saw the object originally here and you see the object again somewhere, right? So that's why we call it symmetric situations. But if you see it only after 360 means it's just nothing, right? It comes to the original status again. So you can call it one fold, but it's really not a symmetric operation in a crystal, right? So two-fold rotation, it's 180 degree. But always you can find out this factor, right? If you see three times the same object over a 360 degree rotation, then what you do is to find out the angle, you can divide it by 3. If it is three times you are seeing, so it should be 120, right? Two-fold, sorry, three-fold, 120, like that. So if you see it in 60 degree, then also you can alternatively see which fold it belongs to, right? So you can simply divide it 360 by the angle that you observe, 60, right? And then you will see it's 6 4, right? Like that, we can define these things. There are some symbols that we use for used in crystallography. Sometimes you may use these things. So you can remember if a symmetric operation is related with mirror plane, then it can be indicated with a symbol M. So if you see in a crystal mention M over a plane, like in a crystal, right? That indicates uh, it's the mirror plane of that particular crystal that defines the symmetry. And if you see a point in a uh, in a crystal called P, that indicates the center of symmetry of that particular crystal, right? So inversion for the symmetry, inversion symmetric operation. Okay, and if you want to show the how many times you can observe the same object over 360-degree rotation period, and then inversion, which we call the roto inversion. For example, if it is fourfold, you can see 4 star, right? So that indicates it's a fourfold rotation and then inversion, right? So that element is called 4 star. So if it is 6 star means 6-fold rotation and then inversion. So this is how you see some of the symmetric operations denoted in diagrams. Okay, so these symbols might be there in some diagrams. So then you should understand which type of symmetric operation they are referring to based on these symbols. All right. Okay. So any questions regarding the symmetric operations? We have to apply uh, this into the crystals now, because now we just learned about the symmetric operations, and we will apply these into crystals. So to apply them into the crystal, sometimes it's important that you have a clear understanding about the crystal lattice, right? So you know lattice is a combination of unit cells, right? Systematic stacking of unit cells, right? You remember in a crystal, you can crystal lattice can be defined like, I mean, simply defined in simple terms like that, right? So when you have a lattice, uh, it's kind of an infinite array actually. It's an infinite array because you can see, for example, here you can see uh, n times these unit cells are together, right? So in a lattice, this periodic arrangement of atoms you can see as an infinite arrangement, right? So if you see still one point here, for example, if you take this point, right, and you see the adjoining point here, here, and you have another one here, another one here. So what do you see? Even here, you see, you can. This is the central location, central point of the face of this crystal, and an edge you see here like this, right? So one is joined here, one is joined there, and one is joined down there, right? So likewise, it's joined with other crystal, other points, right? So if you take uh, a point in the edge like this and a point in the center like this, they have unique surroundings, right? For example, if you take the same point like in the center, in the other face here, or another point in the other another face, they have identical interconnections, surroundings, right? So similarly, if you have uh, other points in the body, I mean, sorry, in the corner, right? So you will see very identical types of surroundings, right? So you have a point and your surrounding is also very identical, right? Wherever you go to a similar place, you will see similar type of and surrounding, right? Without having, I mean, it's very systematic, right? So this type of identical surroundings we call lattice points. So lattice points. So these are points, individual points in the lattice. So you can call them lattice points if they are very systematically arranged. So that means if you have somewhere identical uh, their surroundings, then you can technically term that particular point as lattice point. All the points are not lattice points. Okay, all the points may not be lattice point, but in a cube like here, it's always the same, right? Because it's a very isotropic. So you can't distinguish the lattice points with other points, right? But the face and these points in the center of the face, like these points are different from the edge points anyway. But apart from that, most of the other points are very similar, right? So cube can have so many lattice points, but other crystals might not have that much, right? That many. Okay, so anyway, these are called lattice points. So the overall crystal structure is defined by lattice and something called motif or a basis. Motif or a basis. So this motif or basis means how these lattice points are arranged, right? How these lattice points are arranged is called a motif. So overall lattice plus how it is arranged means the crystal structure, right? The lattice should be there defined by a unit cell, and there should be a way of stacking them, arrangement. So all this configuration we call a crystal structure. So crystal structure is defined as a combination of a lattice plus uh, the motif, okay, the unit cell and its arrangement. Right. So in the unit cell, if each point, each lattice point is arranged with or defined with some atoms, right? You can see a complete crystal structure is generated there, right? So these are atoms or ions, right? Depending on whatever the species, chemical species or physical matter, right? So this stacking is called the entire crystal. So this is what you call the crystal, okay? Lattice plus motif. So lattice is internal, so you have the lattice inside this crystal structure, and it's arranged with atoms placed on lattice points. Remember, all the atoms are placed on these lattice points, so then only you can define it as a crystal, okay? So this is just the lattice, right? And when you arrange it with atoms, you can call it crystal structure that gives you an image or picture like this, okay? So this is one of the examples, right? So this is how we define crystal structures and lattice. So lattice and crystal structure is two things, two things, but maybe very closely equal, closely related. uh, when atoms or ions are uh, placed on lattice points, then you call it, that structure, a crystal structure, okay? So this is how the crystals are generated. Again, we will go back to the smallest repetitive unit, right? Smallest repetitive unit, because you can have several repetitive units in a crystal lattice, right? So you take this type of thing, you can have different repetitive units. If you take this as an example, right? You can have this unit as the repetition, because you see another unit is there, or you can have this unit, this small unit, as repetitive unit. So this means any crystal structure may have, I mean not all, but some may have several repetitive units, right? For example, in this case, you can take this as the repetitive unit. At the same time, you can take this triangular shaped thing as a repetitive unit also, right? Like here, okay? It's also repeating, right? So then we have to select the smallest repeating unit, the smallest repeating unit as the unit cell. That's why we define the unit cell in that manner, right? So always remember, when you select the unit cell, you might be asked to find out the unit cell giving different patterns. Then you have to select the smallest one, okay? Smallest means it may have high symmetry, right? The bigger means you are getting low symmetry, right? When you make the shape complicated means you are losing the symmetry, right? When you make it more simple and more smaller, that means you are getting more and more symmetries, right? So that's why this unit cell is defined as the highest symmetry object which repeats over the lattice, right? So we talked about the translation also, right? So you can take this unit cell uh, to move to this place, that is translation, right? Again, you have the same shape. So what is this? This is translation symmetry, right? We discussed this before. So this is translation symmetry that should be applied, or could be applied to the atomic scale, right? Symmetry of a crystal should be uh, penetrative. That means not the macroscopic crystal itself, but it should go up to the smallest unit also, right? Even individual units of this unit cell can be uh, repeated, right? Translated, right? When you move uh, equal distances, remember we have to move the equal distances, right? Otherwise you can move it here and the other one there, so then you will not preserve any symmetry, right? So it should be systematic translation, right? Systematic movement. that will provide you a translation symmetry for the crystal. So this should be available in the atomic scale, right? So we discussed previously about the identical surrounding, right? So you have a point, you take a point, and you look about the surrounding, right? So if you have the identical surroundings, for example, if you take this point, red point here, right? And what is its surrounding? Here triangle, here square, and here star. So if you compare it with this place and compare it with this place and compare it with this place, what do you see? Very identical locations, right? So surrounding is same, identical. So therefore, you can take it as uh, lattice points, right? Lattice point we defined as points where you have identical interconnections, right? So this type of points you can take as the identical lattice point. So you can see the unit cell, unit cells are arranged over the lattice points, right? Unit cells are arranged over the lattice point, right? So this is important. So translation symmetry also you can define there because you are if you move the entire unit cell in a given distance, right, constant distance like this, then you will produce the same lattice structure, right? So that means you have the translational symmetry by moving from one lattice point to another lattice point, right? From one lattice point to another lattice points. So these lattice points have some constant distances, right? Defined in angstroms. These distances are constant, right? For individual crystals, different crystals, they have different lengths. All right. So these are lattice points which define identical surroundings, and they can be used to show the translational symmetry. Okay, so we talked about previously about the motif or the basis. So it's the arrangement of the unit cells over lattice points, right? When you put atoms on the lattice points, for example, these are lattice points, right? You have the lattice points there. Hmm? These are the lattice points. So when you put uh, atoms over the lattice point, that means when you arrange them according to basis or motif, then you get finally the crystal structure, right? So the same idea that we discussed, right? So primitive lattice means the unit cell, right? When you put atoms over the lattice points there, you can have the crystal structure produced. Okay, so this is a three-dimensional arrangement. Okay, do you have any questions? Because this idea is very important. Unit cell and lattice points are very, very important. So another example, if you can't remember the choosing how to choose the how to choose the unit cell, you just keep in mind this type of an image, right? A number of circles there, right? Like a mesh like thing, and there you can draw many patterns, right? You can draw many patterns. Okay, see, many patterns can be drawn. So you can draw patterns, similar patterns like this, right? Many patterns can be drawn. And the smallest pattern you can draw is like this. Okay, this is the smallest pattern that you can draw there, right? So then you take that smallest pattern as a unit cell. So if you can remember this mesh, then you can easily find out, try to locate the unit cell there. Okay, so atoms, and also the other point is atoms are placed on each lattice point. Atoms are placed on each lattice point. So all the situations will produce similar configurations, right? Similar configurations by reproduction of this lattice, sorry, the unit cell, right? Unit cell in all three-dimensional directions should be able to provide you the same symmetry, right? Even though you uh, moved it. So it's a simplest type of a structural unit. Okay, right. So it's actually a symmetric unit. It's a symmetric unit that define in a crystal, right? So this is a cubic lattice and this is cubic crystal, right? Lattice is just having lattice points only according to the shape, but the crystal will have the motif overlying it, right? That means atoms or ions are replaced there on lattice points, placed on each lattice point, right? So this is about the, the results of symmetric operations, right? It's a kind of a result of symmetric operation because that we use to test the crystal whether you can get a particular symmetry, right? In a case like cube, you have all types of symmetries easily, rotational, translational, point to anything, right? But all crystals will not have that symmetry, right? For example, if you have something in this shape, it won't have all symmetries, right? It won't have all the types of symmetries, but cube can have any type of symmetry and also a sphere, right? A sphere can have any type of symmetry. So a cube and spheres are giving perfect symmetric configurations. All right. So, do you have any questions up to now? So these symmetric operations are very important, right? So remember to how you can find out the n-fold symmetries, right? So always these n-fold symmetries can be uh, produced after rotation of 360 degree. Then count how many times you see the uh, same configuration of the crystal, right? Then if it is 2, then you divide 360 by 2, that means 180. That every 180 degree you see that, right? So likewise, you can find out two-fold, three-fold, four-fold, like that, the symmetries, right? You just rotate this crystal in your hand and see at which angle when you rotate you see the same configuration, and then you check uh, the number of times. So then you can define n-fold symmetry, right? Because rotation symmetry is very important because you can't expect all the crystals like cubes or spheres, right? They are very easy, but there are very complicated crystals. Their symmetries are very difficult. The symmetry is hidden inside the crystal, so it's not an easy task to find out the symmetry. Uh, therefore, therefore, you can find you can check n-fold symmetry by looking at the angle and the number of times, right? Okay. Someone has sent a message here in the chat box. So we couldn't find the window to submit the assignment in the LMS. Don't you find a place to submit? No link, no place to upload or anything? Okay, I will check. I will check and let you know. Otherwise, some of you had sent me by email, so you can continue by sending an email, right? For the time being, I will check the LMS anyway. All right. So if no questions, we can stop the lecture today, and make sure that you submit the assignment on time. Okay, right? By email is okay for the time being. Okay, see you or tomorrow. Tomorrow I might not take the class because I have a university meeting there. If Dr. Navisha Korlager is available, she might take the class, right? So she will send you a message with the link if she is taking the class. I'm not taking the class, right? Okay, so I will be continuing on Wednesday. All right. Have a nice day.